The Norwegian Sea in December operates at the intersection of several forces that have no interest in the ships that navigate between them. The polar front sits at approximately 68 degrees north this time of year, separating the relatively milder Atlantic air mass to the south from the continental Arctic air that presses down from the north and east. At 3:47 a.m. on December 9th, USS Ross is at 71 degrees north latitude, 290 nautical miles west-northwest of Tromsø, where the Atlantic influence has retreated and the Arctic influence has arrived fully. The air temperature at the surface is -19 degrees Celsius. The wind from the northeast at 18 knots has pushed the effective temperature to approximately -34 degrees Celsius. The sea state is a moderate 3 to 4 meter swell from the northwest, long period, the remnant of a storm system that crossed this area 36 hours ago. The visibility is 12 nautical miles in a sky that is black and clear and indifferent. USS Ross makes 19 knots on a southwesterly heading, transiting the Norwegian Sea egress corridor after completing a Northern Fleet surveillance operation. She has been at general quarters for 33 minutes. The intelligence picture in the past 72 hours has assessed the Northern Fleet's Zircon-capable surface group as conducting what the community characterizes as a deterrence posture demonstration, operating within range of the egress corridor without maneuvering aggressively. A tactical behavior that falls short of an engagement posture, but is not passive. At 3:14 a.m., the EW operator classified a radar emission from the group's direction as consistent with a Zircon pre-launch targeting sequence, and the commanding officer called GQ. At 3:26 a.m., the Zircon launched. The Ross's SM-6 engages the Zircon at 41 miles. The SM-6's intercept is a proximity detonation at 11 meters. The Zircon's Mach 8 terminal approach compresses the engagement timeline severely, and an 11-meter proximity detonation represents a successful, but not absolute intercept. The Zircon's guidance section and warhead are disabled. The airframe continues toward the Ross at Mach 6, fragmented but moving. The second SM-6 achieves a secondary intercept at 19 miles that disperses the largest fragments. The debris field passes over and clear of the Ross. No fragments impact the ship. The shockwave from the Zircon's SM-6 intercept at 41 miles reaches the Ross at 3:47:11 a.m. It is a more powerful shockwave than the Chaffee encountered from its Onyx intercept. The Zircon travels at Mach 8 and carries a substantially higher kinetic energy budget than the Onyx at Mach 2.5. The shockwave overpressure at 41 miles is approximately 0.9 psi, more than twice the Chaffee's experience, and approaching the lower boundary of equipment disruption for some sensitive systems. The three gas turbine generators, GTG-1, GTG-2, and GTG-3, each have vibration-sensing protection systems that trip the generator offline when shaft vibration exceeds a specified threshold. This protection exists to prevent bearing damage in a generator experiencing abnormal mechanical loads. The vibration threshold is calibrated for normal ship operating conditions, wave action, propeller imbalance, the structural resonances of a ship at speed. It is not calibrated for 0.9 ps. A shockwave overpressure arriving as a single impulse at 3:47:11 a.m. All three GTGs trip simultaneously at 3:47:11 a.m. Total blackout. The ship's electrical systems drop to zero in the time it takes for the bus voltage to decay, approximately 0.4 seconds. The emergency diesel generator activates automatically as designed. It receives the loss of main power signal and begins its start sequence. Emergency lighting shifts to battery backup. The sound of the ship changes. The ventilation fans, the pump motors, the hundreds of small electrical loads that run continuously on a warship falls silent in the specific way that only total power loss produces. In the engineering spaces, the silence is followed immediately by the sound of the ship's movement. the structural creaking, the water against the hull, the wind outside, sounds that are normally masked by machinery noise and that emerge in a blackout as the ship's own voice. The emergency diesel generator is designed to restore power to critical ship systems within 30 seconds of main power loss. It is a 750 kilowatt diesel generator located in the emergency generator room on the 02 deck, fed by a dedicated 500-liter fuel tank in the generator room and connected to the ship's emergency power bus through automatic transfer switches. It provides enough power for emergency lighting, fire pumps, basic communications, and the engineering systems needed to restart the GTGs. It does not power the Aegis radar. It does not power the VLS, but it powers what the engineering team needs to restore main power, and it starts in approximately 22 seconds under normal conditions. The emergency diesel generator does not start at 3:47:33 a.m., 22 seconds after the blackout, when the generator should have completed its start sequence and been transferring power to the emergency bus. The engineering watch in the generator room reports on the sound-powered phone. Generator cranks but will not fire, repeating start attempts. The chief engineer is in DC Central on the sound-powered phone at 3:47:36 a.m. What is the status? Cranks normally. Fuel delivery appears normal from the fuel solenoid indicator. Starter motor engages. No ignition. The chief engineer recognizes the symptom in 4 seconds. He has serviced this generator. He has read its maintenance records. He has walked the generator room. The emergency diesel generator's fuel supply runs from its dedicated tank through a spin-on fuel filter that is mounted on the starboard side of the generator at approximately deck level, an accessible location for routine maintenance, which is part of why it is positioned there. The fuel filter is a cartridge-type assembly with a cast aluminum housing. The housing contains a filter element and a small fuel gallery. The volume of fuel between the tank connection and the engine's injection pump inlet at -19 degrees Celsius exterior. With the ship at general quarters and the normal heating system dependent on electrical power that is no longer available. The temperature in the emergency generator room has been declining since the blackout. It was at a workable temperature when the blackout occurred. In 22 seconds, the room temperature has not yet dropped significantly, but the fuel filter housing, which is mounted on the starboard bulkhead, the outer bulkhead, closest to the ship's exterior, has been accumulating cold from the Arctic air on the other side of the steel for the entire duration of the voyage. The ship's heating has been keeping it above freezing during the transit. That heating stopped 22 seconds ago. The fuel filter housing is not frozen, not yet. But the JP5 diesel fuel in the fuel gallery inside the housing has been at the filter's ambient temperature, cold but fluid, for the entire transit. In the 22 seconds since the heating stopped, the fuel gallery temperature has not changed meaningfully. The fuel is still fluid. But this is not the problem the chief engineer is thinking about. He is thinking about the previous 12 minutes. At 3:35 a.m., 12 minutes before the blackout, the watch in the main engine room reported a minor coolant leak at the heat exchanger connection on the port main engine cooling circuit. The report was logged as non-critical. A weeping seal, approximately 0.3 liters per hour, within the acceptable range for a ship at sea. The coolant was engine coolant, a water glycol mixture, leaking from the heat exchanger onto the engine room deck. At normal operating temperatures, the coolant drains into the bilge and is pumped out routinely at -19 degrees Celsius. With the heating now off, the coolant that leaked onto the port engine room deck in the 12 minutes before the blackout has collected in the low point of the engine room bilge at approximately 0.4 liters. At -19 degrees Celsius, water glycol mixture at a 50-50 concentration freezes at approximately -37 degrees Celsius. It will not freeze quickly at -19, but the coolant that leaked onto the deck plates in the engine room has run from the deck plates to the lowest accessible void under the deck grating, which is an uninsulated metal channel approximately 30 centimeters wide and 15 centimeters deep, running along the port engine room bilge. In that channel, the coolant has pooled and is now freezing from the surface down as the unheated engine room loses temperature through the uninsulated bilge structure. That is a problem for the future. The immediate problem is the fuel filter. The chief engineer knows what happened to the fuel filter. Not because he can see it, but because he has been in the emergency generator room in exactly these conditions, and he has read the generator's cold weather operations note. The fuel filter housing, the cast aluminum housing on the starboard bulkhead, has a design characteristic that creates a specific cold weather vulnerability. The fuel gallery inside the housing, which is approximately 80 milliliters of fuel volume, is surrounded by aluminum on all sides. Aluminum has a high thermal conductivity. The starboard bulkhead behind the filter housing is in contact with the exterior shell of the ship's hull superstructure on its other face. At -19 Celsius exterior, the outer shell temperature of the starboard bulkhead in the generator room is approximately -12 Celsius at its inner face. The fuel filter housing, in contact with that bulkhead, is approximately -9 Celsius after a 290 nautical mile transit through Arctic air. The fuel in the filter gallery is at -9 Celsius, close to but above the pour point of JP5, which is approximately -51 Celsius. So the fuel itself is not frozen, but at -9 degrees Celsius, the wax crystals in the JP5 that exist naturally in the fuel have partially precipitated out of solution and are coating the filter element. The filter element is wax blocked. The fuel cannot flow through it. The engine cannot receive fuel. The engine will not start. This is not a condition that appears on any instrument. It produces the same symptom as an empty fuel tank, a stuck solenoid, or a failed injection pump. No ignition. But the diagnosis is different, and the fix is different. He calls the generator room at 3:47:52 a.m. The fuel filter is wax blocked from cold. The housing on the starboard bulkhead has been cold for the entire transit, and the fuel element is blocked. I need you to warm the filter housing. It needs to reach approximately +5 Celsius to allow the wax crystals to dissolve and restore fuel flow. I estimate approximately 3 minutes of heat application to restore flow. The generator room watch responds. Chief, heating strips are on the electrical bus that's down. Portable heat gun is in the engineering equipment locker, but it also needs power. I have a battle lantern, a set of hand tools, and whatever is in this room. The chief engineer has thought through this before the response arrives. In the emergency generator room, without electrical power, the options for applying heat to a cast aluminum fuel filter housing are body heat, holding the housing, which at -9 Celsius will transfer heat slowly, approximately 0.5 degrees per minute, taking approximately 28 minutes to reach +5. Not acceptable. Chemical heat packs, emergency warming packs from the first aid kit, which produce approximately 40 degrees Celsius of heat from an exothermic chemical reaction, which are in the medical locker, not the generator room, and require someone to physically retrieve them. That is approximately 4 minutes of transit time through the ship in darkness. Not ideal, but possible. The third option is the one the chief engineer will not choose unless there is no other. The emergency generator room's fire extinguisher cabinet contains a 1 kilogram propane torch, a standard plumber's torch stored for heat shrink fitting and pipework in the engineering spaces. Propane torch heat applied to an aluminum fuel filter housing will warm the housing rapidly. The propane flame at approximately 1,900 degrees Celsius, applied carefully to the housing exterior at a distance, produces controlled radiant heating. The fuel inside the housing is JP5. The filter housing is sealed. The propane torch, applied to the external aluminum surface and not to the fuel inlet or outlet connections, does not introduce flame to the fuel directly, but JP5 has a flash point of 38 degrees Celsius. If the housing is heated unevenly, if the exterior reaches a temperature that allows fuel vapor to escape from a fitting connection and contact the open propane flame, the fuel in the filter housing ignites. In the emergency generator room, with the 500-liter fuel tank 6 feet away, ignition is not an inconvenience. It is a catastrophe. He calls DC Central on the sound-powered phone. I need someone from the medical locker to the emergency generator room with chemical heat packs. How long? The DC Central watch responds. Medical locker is through 2-condition zebra watertight doors. 4 minutes minimum. He is calculating simultaneously. 4 minutes to get the heat packs. 3 minutes to warm the filter. Total, 7 minutes from now to generator start. The GTGs are available for restart. They tripped on vibration protection, not on a mechanical failure. And a hot restart of a GTG takes approximately 3 to 5 minutes once normal power is available. Total time from now to main power restoration, 12 minutes minimum, probably 14. Without power, the ship has no defensive radar, no Aegis, no VLS. The Northern Fleet's surface group that fired the Zircon has not detargeted. The EW operator, working on battery backup communications, reported at 3:47:25 a.m. that the targeting radar is still active. If a second Zircon launches in the next 12 to 14 minutes, the Ross cannot engage it. He calls the generator room. Use the heat packs when they arrive. Do not use the propane torch. I know it is in the cabinet. Do not use it. Hold position. He calls DC Central. Get the heat packs moving now. And tell me what the GTG restart time is from a hot trip. He already knows the answer, but he wants it confirmed. The engineering watch confirms. 5 minutes for GTG3. The quickest restart path. It is the smallest of the 3 generators and has the fastest air start sequence. 5 minutes from power on to GTG3 online. He recalculates. Heat packs arrive in 4 minutes. Filter warming takes 3 minutes. GTG3 restart takes 5 minutes. Sequential, 12 minutes total. Parallel option. Start the GTG3 air start sequence on battery power. The air start system is connected to high-pressure air bottles that retain their charge independent of electrical power, while the heat packs are being applied to the filter. The air start sequence prepositions the starter for immediate engagement when fuel flow is restored. This takes approximately 2 minutes of air start preparation that runs simultaneously with the filter warming. If the filter warming takes 3 minutes and the air start preparation takes 2 minutes, with both running in parallel, the GTG3 can engage within approximately 3 minutes of the filter being warm enough to pass fuel, reducing the total time from 12 minutes to approximately 9. He calls the generator room at 3:41 a.m. While you wait for the heat packs, start the GTG3 air start preparation sequence on battery power. Position the air start valve, pre-stage the ignition, run the pre-start checks on battery power. When the filter is warm and the fuel is flowing, I want to be ready to engage the starter immediately. The damage controlman arrives at the generator room with 4 chemical heat packs at 3:52:14 a.m. 4 minutes and 22 seconds after the blackout, which is approximately 30 seconds faster than estimated, because the condition zebra watertight doors were operated efficiently. The chemical heat packs are standard military-issue disposable heat packs, each rated at 54 degrees Celsius for approximately 1 hour. He applies 2 heat packs to the fuel filter housing, securing them against the housing with a strip of duct tape from the tool kit, and begins applying the remaining 2 by hand, holding them against the housing surface to accelerate heat transfer. The fuel filter housing temperature begins rising. The initial temperature of the housing, measured by touch after 1 minute of heat pack application, has risen noticeably. From the cold metal sensation of -9 Celsius to a warmth that suggests the housing surface is approaching 15 to 20 Celsius. The wax crystals in the fuel gallery, which melts progressively as the temperature rises through their melting range, are beginning to dissolve back into solution at 3:53:47 a.m., 93 seconds after the heat packs were applied. The generator room watch attempts a start. Crank. Fuel solenoid opens. Starter motor engages. Hesitation. The engine catches at 3:53:52 a.m. A preliminary ignition, unsteady, running on partial fuel flow as the last of the wax crystals in the filter element clear. By 3:53:58 a.m., the engine is running steadily. The generator room watch reports. Generator running. Speed stable. Ready for transfer. The GTG-3 air start sequence, which the watch began at 3:48:41 a.m. and has been held in the pre-start position state, is engaged at 3:53:52 a.m. simultaneously with the emergency generator reaching stable output. GTG-3's air start motor engages the turbine shaft at 3:53:55 a.m. The hot restart sequence for GTG-3, which tripped on vibration protection rather than on a thermal or mechanical fault, requires the turbine to spool from zero to idle, pass through the ignition light-off sequence, and accelerate to generating speed. At 3:55:41 a.m. GTG-3 reaches generating speed and is connected to the main bus at 3:55:49 a.m. Main power is restored. The total blackout duration, 8 minutes and 38 seconds. The Aegis SPY-1D begins its boot sequence at 3:55:51 a.m. The system requires approximately 90 seconds of initialization before returning to full operation. At 3:57:22 a.m., the SPY-1D returns to active scan. The EW operator, who has been tracking the Northern Fleet Surface Group on battery-backed passive sensors throughout the blackout, reports at 3:57:31 a.m. Targeting radar has gone to standby. Group appears to be holding position. No additional launch indications. The Northern Fleet Surface Group did not fire a second Zircon during the 8-minute and 38-second blackout window. The debrief will assess this as consistent with the group's observed tactical behavior. The first Zircon launch appeared to have been a deterrence demonstration rather than a committed engagement, and the group may have assessed the Ross's lack of radar emissions during the blackout as evidence that the first launch had achieved its deterrence effect. The tactical calculus is not certain. What is certain is that no second Zircon arrived. The bilge coolant situation, the 0.4 liters of water glycol mixture that began freezing in the port engine room bilge channel during the blackout, is assessed at 4:01 a.m. when the engineering watch enters the port engine room with a portable light. The mixture has partially frozen, forming a 12 centimeter by 8 centimeter ice patch approximately 4 millimeters thick on the bilge channel surface. The ice patch does not block any drainage, does not affect any piping, and melts completely within 20 minutes of the heating system restoration. The coolant leak at the heat exchanger seal that produced it is addressed with a temporary sealant application at 4:23 a.m. and scheduled for permanent seal replacement at Tromsø. The propane torch in the emergency generator room cabinet was not used. The chief engineer was asked at the debrief why he explicitly prohibited the torch when it was the fastest available heat source. He said the fuel filter housing is aluminum, highly thermally conductive, applying a 1,900 degrees Celsius flame to the exterior of a fuel filter housing that contains cold-soaked JP5, even with the filter sealed, creates a risk of uneven heating that exceeds the JP5 flash point at a fitting connection before the fuel in the gallery has warmed. He said the risk is low in absolute terms. He said a low probability catastrophic outcome in the emergency generator room, 6 feet from a 500-liter fuel tank, is not a risk he would accept when a slower alternative is available. He said 4 minutes for the heat packs was the correct choice. He was asked how he made the calculation that led to the parallel path approach. Running the GTG-3 air start preparation simultaneously with the filter warming rather than sequentially. He said the sequential approach was obvious. The parallel approach required 5 seconds of thought, and 5 seconds was available at the moment he made the call. He said the GTG-3 air start preparation on battery power costs nothing in time if the filter warming fails. The preparation can be reset. If the filter warming succeeds, the preparation saves 3 minutes. He said it is a one-sided bet. The Northern Fleet Surface Group did not fire a second Zircon during the 8-minute and 38-second window when the Ross had no radar. He was asked if he knew that at the time. He said no. He said he proceeded on the assumption that a second launch was possible and that the fastest available restoration path was the appropriate response to that assumption. He said the alternative, assuming a second launch was not coming and taking additional time, produces a different outcome if the assumption is wrong. He said he preferred to be wrong about the threat not arriving than to be wrong about the threat arriving while he was moving slowly. One Zircon intercepted at 41 miles at 3:47:11 a.m. Shockwave overpressure at Ross, 0.9 pounds per square inch. All 3 GTGs tripped simultaneously on vibration protection. Total blackout at 3:47:11 a.m. Emergency diesel generator failed to start. Fuel filter wax blocked from cold at -9 Celsius housing temperature. Chemical heat packs retrieved from medical locker and applied at 3:52:14 a.m. GTG-3 air start preparation initiated on battery power at 3:48:41 a.m. in parallel. Emergency generator started at 3:53:52 a.m. GTG-3 online at 3:55:49 a.m. Main power restored. Total blackout duration 8 minutes and 38 seconds. SPY-1D operational at 3:57:22 a.m. Northern Fleet targeting radar went to standby at 3:57:31 a.m. No second Zircon launch. Ship status operational. The propane torch is still in the cabinet. The chemical heat packs that were used have been replaced from the ship's medical stores. The fuel filter housing has been insulated with a thermal wrap of closed-cell foam as a field modification, secured with aluminum tape, reducing its thermal coupling to the starboard bulkhead. The modification adds approximately 11 degrees of thermal insulation to the housing, enough to prevent wax precipitation at all temperatures the ship is likely to encounter in the Norwegian Sea operating area. The modification took the hull technician 40 minutes and cost the Navy approximately $8 in materials. The chief engineer submitted the modification as a maintenance recommendation. It is pending review by the Naval Sea Systems Command's Engineering Directorate. The Directorate has not yet acted on the recommendation. The foam wrap remains on the fuel filter housing. The ship has operated through 2 subsequent Arctic transits without a fuel filter issue. The propane torch has not been needed. The chief engineer's preference is that it remains that way.